This video is about radioactive decay. We'll start by discussing the basics of radioactive decay, and then learn about and compare alpha, beta, and gamma decay. Let's begin with the basics. In order to discuss radioactive decay, we need to define some basic terms. Atomic nucleus, or simply nucleus, is defined as the small, dense region at the center of an atom. The nucleus consists of protons and neutrons. An example of a nucleus is the nucleus of a carbon atom. The nucleus of the most commonly occurring carbon atom contains 6 protons and 6 neutrons. Another word that you will often hear in this topic is nuclei. Nuclei is simply the plural of the word nucleus. A very similar term is nucleon. A nucleon is a component of an atomic nucleus, so it is either a proton or a neutron. Put differently, nucleon is the collective name for protons and neutrons. For instance, we can say that the most commonly occurring carbon atom contains 12 nucleons, 6 protons and 6 neutrons. Our next term is nuclide. It is defined as a species of an atom with a specific number of protons and neutrons in the nucleus. For example, carbon-12 and carbon-13 are different nuclides. The carbon-12 nuclide has 6 protons and 6 neutrons, while a carbon-13 nuclide has 6 protons and 7 neutrons. The focus here is on the composition of the nucleus. Our last word is isotope. Different isotopes of the same element have the same number of protons but a different number of neutrons. So for example, carbon-12 and carbon-13 are 2 different isotopes of the same element, carbon. Don't worry too much if these terms are a bit confusing at the moment. As you work through questions and see these terms in context, it will all start to make more and more sense. Let's talk a bit about nuclide nomenclature. In this topic, you will often come across the name of an element followed by a number. For instance, nickel-58. Nickel is an element from the periodic table, and the number 58 is the mass number or nucleon number of this nuclide. This number shows that there are 58 nucleons, so a total of 58 protons and neutrons, in the nucleus of this nickel nuclide or isotope. We can also denote nickel-58 like this. Here we have a bit more information. 58 still denotes the mass number or nucleon number, while 28 shows the proton number or atomic number. The difference between 58 and 28 is 30, which means that there are 30 neutrons in the nucleus. Finally, let's define radioactive decay. It can be explained as the process by which an unstable atomic nucleus loses energy through radiation. As a result of the decay, the nucleus becomes more stable. 2 more related terms are parent nuclide, which is the nuclide decaying, and daughter nuclide, which is the nuclide or nuclides formed as the result of the decay. There are different types of radioactive decays, in other words, different ways in which an unstable atomic nucleus can lose energy and become more stable. Let's move on to examine these different types of decays. We'll discuss alpha decay, 2 types of beta decays, and gamma decay. Let's begin with alpha decay. During alpha decay, the nuclide emits 2 protons and 2 neutrons. This is basically a helium nucleus. The symbol for the particle emitted during alpha decay is either 42He or 42-alpha. Feel free to use either of these symbols. As a result of the decay, the proton number of the nuclide decreases by 2, and its nucleon number decreases by 4. In this topic, you will often have to solve questions involving decay equations. Here is an example of such an equation for alpha decay. Here, uranium-238 decays into thorium-234 through alpha decay. As you can see, the nucleon number of the nuclide changes from 238 to 234, and its proton number changes from 92 to 90. On the right-hand side of the equation, we also have a helium nucleus or an alpha particle. Of course, total nucleon number on the left is equal to total nucleon number on the right. 238 is equal to 234 plus 4. And this is also true for proton number, since 92 is equal to 90 plus 2. When we talk about decay, we often mention the range of the emitted particles. By range, we mean how far the given particle can travel in different materials. So we say that alpha particles have low penetration ability. There are two main reasons for this. One is that alpha particles are massive when compared to beta and gamma particles. The second reason is that alpha particles have 2 protons, so a charge of positive 2. Therefore, alpha particles easily interact with other particles. As a result, they are absorbed by a thin sheet of paper or a few centimeters of air. In addition, the ionizing ability of alpha particles is very high. Just a reminder that high ionizing ability means that when an alpha particle interacts with an atom, it is likely that the atom will lose an electron or electrons, in other words, become ionized. Next, let's discuss negative beta decay. During negative beta decay, the nuclide emits an electron, which is accompanied by an antineutrino. We will learn more about neutrinos and antineutrinos in subtopic 7.3. Here are the 2 symbols that we use for a negative beta particle. During negative beta decay, a neutron is converted to a proton. Nucleon number is unchanged. An example decay equation for negative beta decay looks like this. The last symbol in the equation, 0, 0 and a V with a small dash on top of it, represents the antineutrino. A beta particle is much lighter than an alpha particle, and it has a charge of -1. Therefore, it has a moderate penetration range and is absorbed by a few millimeters of aluminum or about 25 centimeters of air. Beta particles have a moderately high ionizing ability. The second type of beta decay is positive beta decay. Here, the nuclide emits a positron, which is accompanied by a neutrino. The positron is the antiparticle of the electron. Its charge is +1. We'll learn more about this particle in subtopic 7.3. Here are the 2 symbols that we use for positrons. During positive beta decay, a proton is converted to a neutron. Nucleon number is unchanged. Here is an example equation for positive beta decay. The last symbol in the equation represents the neutrino. The range, the absorption, and the ionizing ability of positive beta decay are the same as for negative beta decay. Finally, let's discuss gamma decay. During gamma decay, the nuclide emits a photon. Here is the symbol for gamma decay. During gamma decay, proton number and nucleon number are unchanged, since the nuclide simply emits energy in form of a photon. An example decay equation looks like this. The small star next to the I on the left-hand side of the equation means that the iodine nuclide is in an excited state and needs to lose energy in order to become more stable. This is exactly what happens during gamma decay. Gamma particles are highly penetrating. They need a few centimeters of lead or a few meters of concrete to be absorbed. Since photons are massless and are uncharged, their ionizing ability is very low. Let's summarize what we have learned in this video. We began by defining some key terms related to radioactive decay. These were the atomic nucleus, or simply nucleus, the nucleon, nuclide, and isotope. Then we defined radioactive decay and looked at nuclide nomenclature. We learned that the number after the name of an element represents its mass number, and that the two numbers next to the element's symbol represent the mass number and the proton number. We finished up by defining parent nuclide and daughter nuclide. Next, we learned about 4 types of decays: alpha decay, negative beta decay, positive beta decay, and gamma decay. As you can see, for each type of decay, we discussed what is emitted by the nuclide, the symbol of the decay, any changes to the proton number and the nucleon number. We provided an example decay equation, and finished up with the range, absorption, and ionizing ability of each decay. This completes our discussion about radioactive decay. In the next video, we'll learn about half-life.